Section 2.6, we're going to talk about combinations and composition of functions. So combination of functions is a little bit of an extension of a function notation that we were using earlier. So that part won't seem so new, and then composition is sort of an an extension also of things that we were using earlier. So it's not really new stuff. It's stuff that we've been doing when we were talking about function notation a little bit. We're just expanding it a little bit more. So we want to talk about domain again of functions because we've done a little bit with domain with looking at graphs and things like that, but we're going to expand on that a little more. We're going to combine functions using algebra, so like adding two functions, multiplying two functions, things like that. And then we're going to do compositions. And once we get to compositions, we're going to talk about domains again. So if a function does not model data or verbal conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. So my function's f, so we want to make sure that f of x, that for every x I put in there, is a real number. So essentially all my x values that give me a output would be part of my domain. So we exclude from a function's domain real numbers that cause division by zero or real numbers that result in an even root, such as a square root of a negative number. Those aren't necessarily the only places we worry about, but for us now with the functions that we have available, this is what we worry about. So for a given x, if f of x is defined, meaning that I put that f in and we actually get the value, so it's not undefined. If in fact it is defined, which is just the opposite of not undefined, so we see what undefined is. Then the given x is in the domain of your function. So that's another way of saying it. So any x value that results in a defined value in my function, so f of x as defined, then that value is part of my domain. So usually the easiest way to do this is look for what's not in my domain. So we want to find this domain of this function. And we've already been doing this a little bit because we were doing this with rational functions. So if I have 5x is divided by x squared minus 49, then this denominator is 0. Then g of x is undefined. So we've talked about that before. So the way we did this last time was that we just took that denominator, we set it equal to 0, then we factored it. Of course, we'll have more techniques going forward, but we factored it, and then we saw that this only equals 0 if x is equal to minus 7 or plus 7. So this is when the denominator is equal to 0. Therefore, x equals plus or minus 7 is not in the domain. Since what we would see is that g of negative 7 and g of 7 are undefined. Because once we have x has to be 7 or negative 7, we'll get 0 in the denominator. That means the function at negative 7 and the function at 7 is undefined. So they can't be in the domain. So we'd say the domain. So we had a couple ways of saying this. The old way of saying this, domain, all real numbers except that x cannot be plus or minus 7. That's one way of saying it. Another way of saying this is we have x such that x cannot be negative 7 or 7. And then there's another way of saying this, which is this. We can just do an interval notation. So if we're thinking about what we're looking at with a number line, we can have any value except negative 7 and 7. So we can have all real numbers going this way. So that would be from negative infinity up to negative 7. Then we would have everything after negative 7 to 7. Just put this here because I know what we're going to get here. So from negative 7 to 7, and then we skip over 7, and then we go from 7 to infinity. So a lot of times we see this as notation we like to use. So this is our interval notation for this, saying that basically we're going up to negative 7, but we're going to skip over it. And then we start on the other side, negative 7 up to 7, we skip over it, and then we go from 7 to infinity. My domain is everything except negative 7 and 7. Now, if we talk about square roots, one of the things that we know about a square root is that the square root of this x is defined if x itself has to be, has to be less than or equal to 0. I was writing that backwards. So I can do the square root of 0 is 0, that's defined. The square root of 4 is 2, that's defined. But I can't do the square root in the real numbers, anyway, of negative 4 because the square root of negative 4 in the real numbers is undefined. So we're saying this is defined in the real numbers, which is what we're looking at. If this is true. We can only do square roots of 0 or positive numbers if we're in the real numbers. So what that means for us is that, go back to the function we have, is that we can make sure that whatever under that radical sign, so this 2x minus 1, that also has to be greater than 0. So g of x is defined in the real numbers if 2x minus 1 is also greater than or equal to 0, because then it makes sure that whatever is under that radical sign is going to be a 0 or a positive value. So this is the only place it can be defined. We just need to take this part here and get some values for that. So therefore, if I take 2x minus 1 equals 0, so we have an inequality and we're just solving it. We're going to add 1 to both sides. An extra line there somehow by accident. There we go. We're going to add the 1 to both sides, so we get x is greater than or equal to positive 1. Then if we divide both sides by 2, we get x has to be greater than or equal to 1/2. So therefore, x is greater than or equal to 1/2 of the domain of g of x. Because if we notice, I put back in here, if x is 1/2, then we have 2 times 1/2, which is 1. 1 minus 1 is 0. Square root of 0, that's defined. If x is, say, 1, then we have 2 times 1, which is 2, minus 1, which is also 1. Square root of 1 is 1. So it stays defined as long as I'm over 1/2. If I go below that, like let's say 0, then I would have 0 minus 1, and I'd be doing the square root of minus 1. So the way we'd write this domain, you could use this function notation, x such that x has to be greater than or equal to positive 1/2. Or if we use interval notation, x has to be values that are 1/2 or greater. So we just write the domain of 1/2 to infinity. Bear in mind that when you're trying to find your domain, you're trying to make sure that the function is defined for all values of x. So these are just a couple scenarios to look at. So you might have to think about it a little bit. Like you're going to make sure that whatever your x value is, it makes sure that every part of the function is going to stay defined. The first one's easy. These ones may take a little extra thinking about. Okay, so we'll start with a over here. So a, we got the function f(x) is equal to x minus 3 over x cubed minus 4x. So we want to see where that denominator, that x cubed minus 4x equals 0. So if we factor that, we can factor out an x, and then we have x squared minus 4 equals 0. That means if I break that down, that's x times x minus 2 times x plus 2 equals 0. So this is going to be, that denominator is 0 when either x is 0, 2, or negative 2. Okay. So my domain of f(x) is going to be, x can be anything except x cannot be -2, 0, or 2. Or if we do it with the interval notation, then we start at negative infinity, then we hit -2, then we go after 2, and then the next value we have to stop at is 0, because we don't have a value at 0, so we get to the other side of 0, and we go to 2, and then after we skip over 2, we go to infinity. So like, either one of these could be correct. You might see a little fiddling with this one, like you might see x is a real number such that x cannot be -2, 0, or 2. But that's sort of like the shorthand version. Now if we look at B, so B has a problem that we have two radical expressions making up our equation. So we got g of x is equal to square root of x plus 3 plus square root of x minus 3, or minus 2. We want to know, when is square root of x plus 3 and square root of x minus 2 defined? So here's a little difference here is that A, when you're trying to figure out when the denominator is 0, you're looking for it's undefined. B, when you're looking at radicals, then you're trying to figure out where the function is defined. So we have to kind of flip around a little bit depending what we're doing. So we know these are only going to be defined as long as the radicand is greater than or equal to 0. So if we solve these, so we subtract 3 from both sides, and then we subtract here 2 from both sides, we have this situation here. When x plus 3 is defined, as long as my x values are greater than -3, square root of x minus 2 is defined as long as my x values are greater than 2. So we need where g of x is defined. So what you're going to do is you need to make sure that both of these expressions here are defined. We just put a little thought into this. So if x is -3, then this part here is undefined. So that's an issue. We can't have X values that are less than 2 here or it's undefined. Here, we can go below 2, but we know that 2 is okay. Another way to think about it is like this. Here's our number line. We have 2 scenarios here. We need values that are greater than 2 or 2 and greater. But the other one needs values that are -3 or greater. So what we do is we just actually just take the little part here because that's where both expressions are defined. This is where both my radicals are defined. And I'd say that my domain of g of x is going to be, you say x such that x has to be greater than or equal to 2, or you can write in this interval notation 2 or greater. Okay, let's see if we can fit 3 here right along the edge. So C, we have a radical that we have to look at, and we have to look at a denominator. Let's look at the radical first. So for the radical part, we got square root of x minus 3. So we need to know when x minus 3 will be equal to or greater than 0. If we look at that, well, we just see if we add sum to both sides, this part stays defined as long as x is greater than 7. So that's when you look at the radical. Now, if we look at the denominator, that's also square root of x minus 7, but this time we just don't want it to be 0. When does that equal 0? Well, that equals 0 when x is equal to 7. So this needs to be removed. So in these cases where we have, oops, got a typo over here. I might have made this mistake earlier, but just point this out. This, because we included that too, that's a bracket. So we include that too. We don't include these twos, but we included this one. So here what would happen is we're not going to include that 7. I just looked over and realized I didn't include it. Domain of h of x is going to be 7 to infinity. So basically we just take this x has to be greater than or equal to 7, but we say here x cannot be 7. We just remove it from my domain. So my domain has to be from 7 to infinity. Okay. I mean, the worst part of this, the rest of this goes much smoother. So if f and g are two functions, then the sum f plus g, the difference f minus g, the product f times g, and the quotient f divided by g are functions as well, whose domain are the set of all real numbers common to the domains of f and g. And then there's a little tweak to it here in a second. So the function notation is, we got fx as a function, you have g of x as a function. So if we combine them, we will say f plus g, parentheses, and then x. So that means that we took f of x and we added it to g of x. If we do the difference, we do the parentheses f minus g, parentheses x. And then that is f of x minus g of x. If we do the product, that's the f times g in parentheses and then parentheses x, which is done f of x times g of x. And then the quotient is f over g in parentheses, then parentheses x, and that is equal to f of x over g of x. And then we have this additional condition here that g cannot be equal to 0. This is the only time where we're going to really have an issue with the domain. The other ones are going to be much simpler. So if we're going to find two functions here, we're going to have the functions f of x is x minus 5. And that was a typo. That was supposed to be g of x. And g of x is x squared minus 1. We want to find f plus g of x, f minus g of x, f times g of x, and f divided by g of x, and then determine the domain. So I'm going to give you a little trick for the domain. You could look for the domain of the function originally, because if you do, we would see that the domain here, let's write it off to the side. The domain of fx, x minus 5. So here we don't have a radical and we don't have a square root to worry about. So this one here is defined on all real numbers. Or you might say negative infinity to infinity. And you're going to see the same thing, the domain of g of x, which is just x squared minus 1, same thing. I don't have a denominator to worry about with an x in it. I do not have a square root to worry about. So this once again is all real numbers. So we're not really used to that one. We don't see all real numbers very much here. We've been looking at the ones with weirder domains. I'm gonna make this next part easy. So we only have to worry for the most part about what's left out of one of those domains, but since they're all real numbers, the domains that we should see here should also be all real numbers. So I do f plus g of x. That is just f of x plus g of x. So that will be x minus 5, that's my fx, plus x squared minus 1, which is my g of x. And if I simplify this, this is just going to be x squared plus x, negative 5 plus negative 1, minus 6. And once again, we do not have any square roots. We don't have any denominators to worry about. My domain, let's say D, is going to be all real numbers again. So if I do f minus g of x, that's going to be f of x minus g of x, which is going to be, make sure you do this in order because I could flip this and do g first, but this is going to be x minus 5 minus now g of x, which was x squared minus 1. Let's simplify this one. This is just going to be, let's say, negative x squared. So negative x squared plus a positive x, and then we have minus 5 minus minus 1, so that would just be minus 4. And once again, my domain's all real numbers. So we have f times g. That means we're multiplying. Okay, I did put there. Pay attention to that little dot. There's going to be a change we're going to see here. So that is a multiply dot. So we're going to have f of x times g of x. In this case, this is x minus 5 for the f of x times x squared minus 1 for the g of x. So we will have x cubed, if we FOIL, and then minus x, and then we'll have minus 5x squared plus 5, which is going to be, well, I think I can write it after this. Just trying to leave room for my domain. But that'll be x cubed minus 5x squared minus x plus 5. If you want to rewrite it so it is in standard form. And my domain again is all real numbers. All right, so these are all real numbers in this case. I'm going to leave a bit more room for this one. So we could do f divided by g, that's f of x divided by g of x. That is going to be x minus 5 divided by x squared minus 1. And that really doesn't simplify it any further. The problem in this one is just the domains. So notice that all the rest of these, when we look at their domains, the domain is all real numbers. So it's always this one that's a little different. So first three should all have the same domain. If you have the domain of one, you'll have it for the other ones. It's this one's going to be a different domain. And it's not always a different domain, sometimes it is. So is the one you always have to look out for because we know that if we wanted to find the domain, we would have to take that denominator, that x squared minus 1, and we have to figure out when it's equal to 0, which we're going to see very quickly happens when x is either negative 1 or 1. So the domain is going to be from negative infinity up to negative 1, negative 1 to 1, and 1 to infinity. Or you can say all reals except that x cannot be negative 1 or 1. So I was saying, if you have the domain of one of these three, so the sum, the difference, and the multiplication all have the same domain, it's quotient the one that may be different, and it's not always different. Sometimes it has the same domain. Worksheet number 1. So this one, be a little more careful with your domains because it's not going to be all real numbers because you have f of x, which is the square root of x minus 5, and then you have g of x, which is x minus 4. So one of those has a domain of real numbers, but one does not. So when you do your summation, just be careful what your new domain is. Look at your new function and figure out that domain. So when we have these two functions, we have f of x, which is the square root of x minus 5. So its domain has to be 5 or greater. Include that 5. G of x is x minus 4, so its domain is negative infinity to infinity. What we're going to see here is that if I do f plus g, then we're going to have the square root of x minus 5 plus x minus 4. So here, I can't do much to simplify it. This is what it's going to look like, but its domain, we know that this is the only thing that is a problem for this is this radical. So our domain is going to be negative 5 to infinity because I just have to make sure that this radical has the radicand under it stays positive. So all we did is basically we did what we call an intersection of these two. We just saw which one would have to take over. If we do f minus g, I already know the domain of f plus g. I already know the domain of f minus g. But in this case, we're going to have square root of x minus 5, but now we're subtracting negative x minus 4. So it is the square root of x minus 5 minus x plus 4, and its domain is also has to be 5 to infinity. Now if I do f times g, that is going to be the square root of f minus 5 times x minus 4. So you could leave it like that, or you could expand it into this. We're not going to go too involved in like trying to simplify this or anything like that. Got rid of parentheses, maybe that's happy. But once again, the only thing that's a problem is this square root. We need to make sure that what is under the square root stays positive. So my domain again is 5 to infinity. So it's this last one we have to worry about. We have f over g of x. So f of x is square root of x minus 5 divided by x. What was x minus 4? That one we can't simplify, but we know that from the denominator, x cannot be 4. So my domain in this case Remember, we're looking at the top part here is saying that x has to be greater than or equal to 5. So we're looking at this, and then we're saying, but x cannot be 4. Thing is that x being equal to 4 is not even in the domain of x is greater than or equal to 5. So my domain in this case actually stays x is from 5 to infinity. So like I was saying, sometimes the domain stays the same. In this case, if we just looked at the radical, we have to keep values greater than 5, so 4 isn't even a worry. So we have another one. So this is your second worksheet, or sorry, your third worksheet problem. So we have a new set of functions. So once again, one's going to have a domain of all real numbers, but this one's going to have a different domain. So when you make your composition, be careful because you have a radical expression. You have to think about what you need to do to find domains of radical expressions before you actually simplify your function. Okay, so we have, let's write it over here. Let's look at the domain of our two functions. I think it's a little off here. So f of x is just x squared minus 9, no denominator, no radical. Domain is all real numbers. G of x is we have 2x over x minus 3. So we do have a denominator. The only thing that makes the denominator 0 is 3. So its domain is from negative infinity up to 3, and then from 3 to infinity. So the only thing we're doing is we just are going to skip over 3. Remember, this one 3 is not included. If it was a radical, we would include some. Would probably might include a 3. So if I have the functions f plus g of x, remember if I find this one, I have the next two. So this is just going to be x squared minus 9 plus 2x minus x minus 3. And unfortunately, this one doesn't really simplify any down any further. And like a order of powers, kind of. From here, your domain, if you think about it by section, here, I don't have to worry, I don't have a square root or a radical. So this is all real numbers. This one we don't have to worry about because it's constants, it's all real numbers. It's just, once again, this part is causing me the issue. So the only thing I can't have under my domain is 3. My domain is from negative infinity to 3, 3 to infinity. And as we said, the next two will have the same domain. Just want to get these little marks out of the way so we don't have a little extra on our screen. F minus g, you're going to have x squared minus 9, but this time you're going to subtract 2x minus x minus 3, leaving us with x squared minus 2x, x minus 3 minus 9. Once again, the only thing that's a problem is that x cannot be negative 3, or sorry, x cannot be positive 3, so we just remove 3 from the domain. F times g, well, we'll have x squared minus 9, and then we'll have 2x over x minus 3. So this one going to end up being x squared minus 9 times 2x over x minus 3, which is going to be 2x cubed minus, oops, before I do that, let's stop right there. So here we know that the domain is going to be negative infinity to 3, 3 to infinity. So we need to simplify. So I'm going to leave like this because this x squared minus 9 actually just breaks down into x minus 3, x plus 3, 2x, and then we have x minus 3 on the bottom. Our simplified version is just going to be the 2x times x plus 3, or you could say it's going to be 2x squared plus 6x. So let me break this down. So it helps with that little rule that the domain should be the same between the sum, the difference, and the product. Because then if you simplified it, you might think your domain's all real numbers, but once again, you have to remember because it's radical, we need to look at the domain before we simplify, but also it has to match the same domain as the other two. That's the last one that can be a little different though. So hopefully I have the room for this, but we're going to have f over g. So that is going to be x squared minus 9 divided by 2x, x minus 3. So before you even try simplifying, we need, as far as the domain goes, put the domain up here because I'm running out of room on the bottom. We have a denominator with a denominator. So we have this situation. So from this one, we know we don't want x minus 3 to equal 0. We will know that happens, which is when x is equal to 3. But we also need to look at this as a whole. When does 2x, x minus 3 equal 0? So we're not concerned in this case where it's going to equal 0 is when the denominator is going to equal 0. So that's going to happen when x is equal to 0. So as far as the domain goes, two things that we're definitely have to remove from that domain are going to be 0 and 3. My domain will be negative infinity to 0, 0 to 3, 3 to infinity. Okay, make sure I didn't miss something there. Now I can simplify. So we have you can think of it as like this. We are taking a number and then we're dividing by we're dividing by a fraction. So this is, say, x squared minus 9, but we're actually multiplying it by x over 3 over 2x. So this is really x squared minus 9 times x minus 3 over 2x. Oops, popped up on my screen. If I expand this, I'm going to get x cubed. Oops, minus. And let me do this and I'll bring it back here. Okay, sorry, I had to make a little room there to rewrite that. So what you end up getting is x cubed minus 3x squared minus 9x plus 27 over 2x. Domain is from negative infinity to 0, from 0 to 3, and 3 to infinity. So we're excluding 0 and 3. Because if it's 3, then we have a denominator of 0 here. So then we have 2x over 0, which is undefined. If x is 0, then we have 2 times 0 over 3, which is also 0. So we have denominator of 0 again, which is undefined.